While the world takes a little bit of a rest over the Christmas New Year period, we thought we would too, but we're not going to leave you hanging. We've dug into the archives and found a few of the biggest episodes of recent times. So sit back and enjoy those, and we'll be back with new episodes of Space Nuts probably in the middle of January. See you then.
Space Nuts.
Hello, and thank you for joining us on Space Nuts, where we talk astronomy and space science. Great to have your company once again. And coming up on this particular episode, we're going to talk about an exoplanet that has unusual rain. It's raining gemstones and ruby slippers. Well, maybe not the ruby slippers, but definitely gemstones, which is very unusual. We'll also be answering some audience questions. Bob wants to talk about research papers and how accurate or otherwise they might be. That's all to come on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
My name is Andrew Dunkley. I am your host. Thank you for joining us. And with us again this week, because we can't get rid of him really, it is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you?
You are the Space Nuts barnacle. You are. That's
I know. Just a barnacle on the backside of Space Nuts. Dear.
Right, we've got a lot to talk about today, so let's get straight to our first topic, and this is a really interesting one. We've talked about exoplanets and even planets and moons in our own solar system that have unusual kinds of rain, like sulfur rain and acid rain, and I think we talked about a planet once that rained diamonds. Now there's an exoplanet that rains gemstones. What's this all about?
Well, yeah, it's gemstones among other things, and it's there's a lot going on this exoplanet. It's what is it? Well, it is. I think it's a WASP. Yeah, WASP-121b. WASP is a project that detects exoplanets by the transit method, the fact that their brightness drops when they pass in front of their parent star. WASP-121 is actually a star which is about 850 light years from here. It has a planet which is very close to it. It's a hot Jupiter. That's the the official description, because it's a big planet, and it orbits its parent star once every 30 hours. So, its year is 30 hours long, Andrew. It just beggars belief, doesn't it? But that's what's happening. Now, that means one of the things that means is that with a period that short and a distance between the parent star and the planet that small, this planet will be tidally locked to its parent star, and that is the key to understanding what's going on here. It is its day side always is permanently facing the parent star. Well, that's a bit of a tautology, really, isn't it? Because the day side is always facing the parent star. But the bottom line is, this is a good start this morning.
You're going well, Fred.
The bottom line.
See how I bailed you out of that?
Yes. Oh, well done. Thank you. Yes. The planet is rotating at the same rate at which it revolves around its star, like the moon is rotating at the same rate as it revolves around the Earth. And so you've got this one side of it that permanently faces the heat source. And that means one side is hot and the other side is cold. Now, given that we can't see these planets directly, you may well ask, Andrew, how can you study the day and night sides of a world like this in detail?
That's a good question. Glad I thought of it.
I'm glad you thought of it too. The answer is it's really clever stuff and needs, it needs really quite significant astronomical infrastructure in order to make these observations. I should mention that the authors of this work come from MIT, Massachusetts Institute of Technology, Johns Hopkins University, Caltech, and other US universities.
It is a mouthful, but it is Massachusetts.
Massachusetts is what I tried to say. That's right. I didn't really. Anyway, never mind. I didn't do well with it. But so how do you detect what's going on the day and night sides of a world like this? And what you do is you observe the planet, and all you can see is the star. That's the only thing that is visible in your telescope.
Yeah.
But you observe the star's light throughout the orbital period of the planet. And given that that's only 30 hours, you don't have to wait very long. If you were looking from outside the solar system and trying to do this with Jupiter, you'd be waiting, 12 years or something like that? It's much longer. No, I think it's 5 years. Sorry, I should do that calculation again. Anyway, 30 hours gives you time to, to actually work out exactly what's going on through the different phases of the planet, because that's what it's all about. It's like the phases of the moon. We watch the moon going round because it's lit up by the sun. And we can see, it progressing from new moon to first quarter to full moon and all the rest of it. And you can do the same thing with an exoplanet. But all you're able to measure is the total light from the planet plus the star. But as you'd imagine, that varies throughout the revolution period of the planet. When the planet is behind the star, all you've got is the light of the star. And I should add that you're not just observing how bright it is, you're also observing the spectrum of this thing. So you're looking in detail at the chemical constituents that is revealed by the light that is coming to you. Yeah. So when the planet's behind the star, all you're seeing is the light of the star. When the planet shifts slightly in its path around the star, so you can see both, what you've got is effectively you're looking at the full planet, like an equivalent of a full moon. It's almost completely illuminated. Right. And that light adds to the light of the star. And so you can then look at how the spectrum has changed. And that is telling you about the atmosphere of the planet itself rather than the atmosphere of the star. In fact, what you can do is subtract the star spectrum from the spectrum of the combined planet plus star, and you get the planet spectrum. That's how this works, and then that changes throughout the planet's year of 30 hours, and eventually you're looking at the backside of the planet, and in fact you have a point where that is superimposed on the star. Once again, you can do some clever work because you can look at you can look at the combined spectrum of the backside of the planet superimposed on the star itself. That combined spectrum, if you subtract out the spectrum of the star itself, it shows you what chemical constituents again are in the atmosphere of the planet, because the light of the star is passing through the atmosphere of the planet, round the edge of it, and coming back to Earth. So that's the technique. And what's been found is that this object is quite extraordinary. So it's got a day side that is extremely hot, more than 3,000 degrees Kelvin. So what that does is it's known that there is water vapor in the atmosphere of this planet. Well, there's water vapor on the night side, but on the day side, the water molecules are just torn apart because of the high temperatures. So you've got hydrogen and oxygen atoms that are they're independent within the atmosphere. And then it turns out that because of the heat, that generates high pressure in the day side, which causes winds that blow things around to the night side. And on the night side, it's cool enough, for these things to form back to water. And so you get water vapor forming in the atmosphere of the dark side of the planet. They estimate that these winds are 5 kilometers per second. Ooh. So this is 11,000 miles per hour. It's 16 16 or 17,000 kilometers per hour.
Sounds like that's the same as it was in Sydney yesterday.
Yeah, we didn't get the wind, but we got the rain. So we got the water vapor. Huge quantities of rain. Oh gosh, bucket loads of it. H2O suitably combined back into water vapor.
Yes.
So that's what they get on the dark side of this WASP-121b. But there's more, because it's not just water that's circulating like this. They find that on the night side, the temperature is right to have quite, I guess the best word is exotic, clouds of exotic materials, and iron is one of them, and a mineral that actually is a constituent in gemstones. That's the point that you were making right at the beginning.
Yeah. Well, that's the journalistic hook, isn't it?
It is, absolutely. So, yes, to quote the physics.org report on this, on the way around, exotic rain might be produced, such as liquid gems from the corundum clouds.
Wow.
So, liquid rubies, that'd be quite nice, actually. Well, anyway, really quite remarkable stuff. I should mention that these observations were made with the Hubble Space Telescope. It was one of the spectroscopic cameras on board the Hubble telescope that was used, and fantastic work. Congratulations to the team and to the journalists who are writing about this.
I don't suppose they can tell us exactly what kind of gemstones these might be, or gem
blobs
components.
Yeah, they're suggesting that it could be maybe. Look, I had rubies in my mind, and maybe rubies and sapphires. That's the possibility. Corundum apparently is a mineral that goes towards these gemstones.
So I wasn't far wrong with my ruby slippers analogy.
No, it's a very nice one. I like that very much, yes.
Interesting. All right. That's a fascinating discovery. And if you want to read more about it, you should go to the phys.org website. That's not FIZZ, that's PHYS.org website. It's a fabulous website if you want to catch up on that and many other stories. This is Space Nuts with Andrew Dunkley and, of course, Professor Fred Watson.
3, 2, 1.
Space Nuts.
Now, if you would like to do us a favour, that would be wonderful. You can send your checks to Fred Watson Of course, if you do want to become a patron, you can do that, and that is putting a little bit of money into the kitty to keep the podcast rolling, which you can do via our website. Now, that is totally optional, and thank you to those many patrons that do so through Patreon or Supercast. So that's something that you can do, or you can make one-off donations through the Buy Us a Cup of Coffee button on our website, spacenutspodcast.com. Or if you want to do something that's going to be cost-free and just cost you a bit of time, write a review through whatever podcast platform you happen to use. So that's very helpful as well. So those are some of the options to help support the Space Nuts podcast, and we do appreciate anything anybody does to keep us up and running. Okay, Fred, let's get into our question segment. This is where people who listen to Space Nuts send us all sorts of hyper-intelligent questions that I've got no clue about, but Fred has an inkling. And our first one comes from Bob.
This is Bob from Asheville, North Carolina in the U.S. I have two questions. In 2005, Professor John Ioannidis published a highly influential paper in PLOS Medicine titled, "Why Most Published Research Findings Are False." He makes the argument, and here I'm quoting, that for most study designs and settings, it is more likely for a research claim to be false than true. It's important to note that he was focusing on medical studies, which have less scientific rigor than physics. He does, however, conclude that, and I'm quoting his paper again, that for many current scientific fields, claimed research findings may often be simply accurate measures of the prevailing bias. My first question for Professor Watson is, how often does this happen in your field? Meaning, how often are published research findings actually false because of bias or statistical reasons? My second question is a hypothetical. Medicine changes relatively quickly. For example, peptic ulcers were treated with surgery until 1984, which is when Barry James Marshall, an Australian physician at Royal Perth Hospital, reported that peptic ulcers were caused by a type of bacteria called Helicobacter pylori. Today, ulcers are treated with antibiotics. Professor Watson, suppose you could fast forward 100 or 500 years into the future and look back at cosmology and astro.
And that's where Bob unfortunately got cut off, but we think we've got the nuts and bolts of his question. So we're going to take a stab at it for you, Bob. But yeah, I guess the first part of his question is about scientific papers, research papers, published works, and how maybe they could misinform or not be quite accurate. Is that something that happens?
Look, it's a really interesting question. There are, I don't think there in astronomy there is a strong incentive, perhaps, or reason why people should intentionally misinform. I think that is almost always zero. And what research that does bark up the wrong tree, what research of that kind that there is honest mistakes.
Like the colour of the universe, perhaps.
Yeah, well, that's right. That was an honest mistake. Yeah, which was what was it? It was kind of.
They originally said it was aqua, but it turned out to be beige.
It was beige. That's right. And in fact, I remember when I read that paper, this is probably 10, 15 years ago, and I know the guy who wrote it quite well. I remember when I read that paper thinking, this cannot be the case. You can't have an aqua universe because it's expanding, and, you know, you've got basically a redshift there, and it turned out to be beige, which is redshifted aqua. Anyway, look, the kind of thing that I was thinking of, Andrew, and it might go to the heart of Bob's question, is you remember last year there was a big fuss when people thought that phosphine had been detected in the upper atmosphere of Venus. And phosphine on Earth is generally produced by biological processes. And so I know that the researchers who did that work, and I know some of them, in fact, I talked to one of them afterwards. He's a friend of mine in Hawaii. They were very, very careful to tease out the signal of phosphine from the noise. This was done with quite big radio telescopes. In fact, ALMA was one of them, the Atacama Large Millimeter Array. And it was with reluctance that they mentioned the fact that phosphine's a live product.
Because the popular press jumped all over that.
Yeah, that's right.
There's life on Venus. There's life on Venus.
Yeah, exactly what happened. And, you know, maybe the bias that Bob mentions is there because it's something that we're all kind of trigger happy with. We are urgently trying to seek any evidence of life anywhere else in the universe. Now,
and when you give some elements of the media an inch, they take a mile. That's
true, and that certainly happened in that case. Yeah. My recollection is that the original team still stand by their discovery that it was phosphine, but there was another paper published. It must have been actually the year before last when the phosphine measurement was made, because I think it was early last year that another paper was published showing how the phosphine signature could be mistaken, that it might actually, I think it was something like nitrous oxide. I can't remember. It was something a lot less suggestive of life processes. So I think honest mistakes are made, but yes, there might be a bias there too. Generally,
you'll probably find bias in circumstances where somebody's trying to sell something.
Yeah.
You might get those, studies that are released into certain products that improve your life, and the study turned out to be 10 people at a 5-star resort for a weekend answering a questionnaire.
Yes.
That kind of thing. So, there's a bit of that goes on.
There is, certainly. Less so in astronomy. Astronomy, I think, is partly one thing you're looking for, and you always check this whenever you make a discovery, is how consistent it is with what we already know about the universe. Because often, our discoveries, they're highly forensic. It's all done at distances ranging up to 13 billion light years. Just turning to, and I'm hypothesizing here as to what the second part of Bob's question was, because he got cut off, as you said. But I think he might have been wanting to ask me, what if I fast forwarded 100 years into the future and then look back at 2022, what I would think of as being discoveries that maybe were misleading. And perhaps the one that comes to mind, and it's not through any lack of honesty, this is the best evidence we have so far, is that dark matter exists and that it is a subatomic particle of some kind. That is pointed to through so many different experiments, and there's a self-consistency about it as well with what else we know about the universe.
Yep.
But it could well be that it turns out that it wasn't that. That in the end there is something that we don't understand about physics, and what I'm thinking of is MOND, modified Newtonian dynamics. We've got a friend out there in the audience, Peter Verweyen, who's studying that for his PhD and doing a great job. Just maybe the tide will turn and people will see the evidence for modified Newtonian dynamics, which means that gravity doesn't behave quite the way we thought it did on large scales. That might turn out to be the answer. That would be one I might venture to suggest would be something that in 100 years' time we might look back on and say, we all thought it was dark matter. Yeah, how foolish were we?
Yeah, no, and that's probably not an uncommon scenario. I mean, we hindsight is 2020, and
yes, that's right.
You don't have hindsight until you go forward and look back and go, okay.
All right, that was it. That was why. Yeah. Yes. Yeah.
Of course, we get it right a lot of the time too.
I think we do. I think that's right.
All right, Bob, lovely to hear from you. Thanks for your question.
3, 2, 1.
Space Nuts.
Hello again, Space Nutters. This is Anna from Astronomy Daily, the podcast stopping by again with a couple of the important stories we've been following over the past week. In an intriguing start to 2025, residents of Mukuku Village in Kenya's Makueni County were startled by a mysterious arrival from above. A massive metal object, weighing over 1,000 pounds, plummeted from space and landed in their community, creating a sound that could be heard up to 30 miles away. The Kenya Space Agency quickly responded to the incident, arriving at the scene on Tuesday morning. Working alongside local authorities, they secured the area and retrieved what they later identified as a separation ring from a rocket launch. This impressive piece of space hardware measures approximately 8 feet in diameter. Typically, these separation rings are designed to either burn up during re-entry into Earth's atmosphere or land safely in unpopulated areas like oceans. This particular landing, while unexpected, fortunately caused no injuries or significant damage. The space agency has assured the public there is no cause for concern and is treating this as an isolated incident. They're handling the situation under international space law protocols, with the object now in their custody for further investigation. It's a remarkable reminder of how space exploration occasionally makes surprising appearances in our everyday lives. Scientists have made an exciting breakthrough in our ability to detect gravitational waves, those subtle ripples in space-time that give us unique insights into cosmic events. Researchers have developed a new technique called optical spring tracking that could dramatically improve how clearly we can detect these elusive waves. The Advanced Laser Interferometer Gravitational Wave Observatory, or ALIGO, uses incredibly sensitive equipment to measure tiny distortions in space-time caused by distant cosmic events. While this technology has already revolutionized our understanding of phenomena like black hole mergers, it faces limitations from what scientists call quantum noise. This new optical spring tracking system works by tuning itself to match the frequency of incoming gravitational waves. In tests, researchers used a microscopic mirror weighing just 50 nanograms, made from carefully layered aluminum gallium arsenide and gallium arsenide. When hit with laser light, this tiny mirror creates an optical spring effect that can be precisely controlled to track and enhance gravitational wave signals. The results have been remarkable. In their proof of concept experiment, the team demonstrated that tracking a signal with this system improved the signal to noise ratio by up to 40 times compared to traditional methods. This means we could potentially detect much fainter gravitational waves from even more distant cosmic events. While implementing this technology in full-scale observatories like LIGO will require overcoming some engineering challenges, the potential benefits are enormous. By enhancing our ability to detect gravitational waves, we might soon be able to observe events from the very earliest moments of our universe, including the mergers of primordial black holes formed shortly after the Big Bang. This advancement represents a significant step forward in our quest to understand the universe's most energetic events and could help unlock mysteries about how our cosmos formed and evolved over billions of years. And that's it from me for this episode of Space Nuts. I'm Anna. Don't forget to visit astronomydaily.io for your daily fix of space and astronomy news updates. We're constantly updating the site with the latest discoveries, mission updates, and cosmic wonders. Until our next adventure through the cosmos, keep looking up and stay curious about the mysteries that surround us in space.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.